Tijana Minic is going to be telling us about visualizing a non-deterministic to deterministic finite-state machine transformation.
Hello everyone, my name is Tijana Minic and I'm an undergrad at Seton Hall University. Today I'm going to be showing you a visualization tool for non-deterministic to deterministic finite-state machine transformation. This is also joint work with Marco from Seton Hall University. So in formal languages and automata theory courses, a great deal of emphasis is placed on constructive proofs. These proofs are very important because they establish the equivalence of different computation models. Algorithms have been developed to transform one computation model into another. For example, NDFA to DFA, NDFA to regular expression to NDFA, so on, so on. Today, our focus is going to be NDFA to DFA transformation. Now, why this transformation? So many students struggle to understand this transformation because of all of its steps. It's easy to get lost because a student has to keep track of multiple things. The reason for this is that the DFA simulates all of the paths in the NDFA. So that can mean, for example, one path in the DFA can represent multiple paths in the NDFA, or one state in the DFA can represent multiple states in the NDFA. Also important to note that one DFA step is commonly referred to as a superstate. Also, one DFA edge can represent multiple edges of the NDFA. Now you can see why it gets confusing for a student to keep track of all of these things while executing it step by step. And our visualization tool solves all three of these by visualizing the addition of the DFA edges one by one, while simultaneously visualizing the corresponding NDFA edges. So before I start, I know Olivia already gave you an introduction to FSM, but I feel obligated to refresh your memory. So FSM is a domain-specific language embedded in Racket that students use to design state machines. And for today's presentation, the relevant machine constructors are going to be make DFA and make NDFA. So both of these constructors have K, which are states of the machine. Sigma is just alphabet. S is the starting state in K. F is a list of final states in K. And finally, delta is a transition relation, which in the case of a DFA has to be a function. Now, the student can provide the optional no-det argument, which if they do, the constructor assumes that delta is already a complete function and it doesn't create a dead state. We also have the observers. So the first five extract the components of these constructors. An SM graph given a machine returns an image of a transition diagram of the machine that we have designed. Now I'm going to demonstrate programming in FSM. So we're going to look at the following example of the machine that accepts all the words in a language that are either empty word, a word that starts with A and is followed by an arbitrary number of A's. I forget I have a pointer in my hands. And a word that starts with A and is followed by an arbitrary number of B's. Now, I'm going to display the transition diagram right away, so this all is a little easier to follow. So first we have our list of states. So we have S, which is the starting state where input has been consumed and it's highlighted in green. Then we have A, B, and F, which in this case are all final states. So if a word ends up in any of those states, it is the word in the language and it gets accepted. So A accepts all the words that start with A and are followed by an arbitrary number of B's. B accepts all the words that start with A and are followed by an arbitrary number of A's, and F accepts empty word. Now here we have transition rules. So as you can see here, for example, if on S you consume an A, you can either end up in A or B, which implies non-determinism, so this is an NDFA. Now, most textbooks use the following NDFA to DFA transformations. So they start with an NDFA, and then they construct a DFA. So they construct it in the following manner. Here, K prime is a list of superstates. Again, a reminder, superstate is just a state in the DFA. So the list of superstates is constructed as a power set of K. Sigma prime is the same. S prime is the starting superstate, and it contains all empties of S, which just is all states reachable from S by empty transition. F prime is a list of final superstates, and they all have to be in K prime, and every superstate has to contain at least one state from the list of final states in the NDFA. And finally, delta prime is list of all transitions from a superstate to a superstate. So, bear with me. For example, if you have some superstate Q that contains some arbitrary state little q, and you consume a y, right here, y, you can end up in some state little p and all of the empties of that little p. Now, all of the little p's that you can end up in and all of their empties, when you put union of them, that's your destination superstate that you end up in. So JFlap is a visualization tool that has developed an NDFA to DFA transformation. And I already here have constructed an NDFA of the same machine that we just looked at that accepts the words that start with A, followed by an arbitrary number of B's, starts with A, followed by an arbitrary number of A's, or just empty word. I'm going to convert to DFA now and show you how JFlap tool works. So here we have Q0, which is the starting state of the constructed DFA. And as you can see here, we have 0 and 3, which are just the numbers of the corresponding states in the NDFA of the superstate. In other words, empties of S, which again is the starting superstate. And now we're going to expand this once. So we expanded this transformation on an A. So on an A in the NDFA, we can either end up in states Q1 or Q2, which here corresponds to these numbers 1 and 2. So this edge in the DFA corresponds to these two edges in the NDFA. Now, we can keep stepping through this, or we can just complete the transformation in one step. So this is the transition diagram that we get. Hold on, let me make it a little smaller. So all of these edges in the DFA correspond to certain edges in the NDFA. Now, this machine is relatively simple. So the transition diagram of the DFA is going to look pretty simple. But if we just do this and slightly change this machine. Hold on. There we go. Got to click through it. So here we're going to add 2 empty transitions. So what I'm doing right now is I'm constructing an NDFA that accepts the words that are missing one of the letters of A, B, or C. So it's either missing a C, a B, or an A. A, B, B, C, A, C. Okay, cool. Now I'm going to convert. So instead of stepping through the entire thing, I'm just going to complete it in one step and show you what we get. This is our transition diagram. Now, a thing about JFlap is if you want to see any part of this computation again, so any step that you step through, you can't go backwards. You would have to do this, and then start again, and then click here, and then expand. So it takes a little bit of time to actually go back and see something that you might have wanted to see. So that is JFlap. Now, OpenFlap is a similar tool with slightly less functionalities, but the haphazard graphs remain a problem. So here again, I'm presenting you the transformation that most textbooks use. So what we decided to do is tweak this transformation a little bit for the following reasons. So what we're bothered with is this. So K prime is a list of superstates, and in this transformation, it is a power set of K. Imagine how many subsets of K you might have if you have a huge NDFA. That's so many superstates that don't even end up being used in the construction of the DFA. So instead of computing the power set of K and going from there, we are going to traverse the computation tree, find the transition function that we're going to encode into the DFA, and just take the superstates that we need. So our transformation is going to look something like this. So we have make DFA, where K prime is the encoding of our superstates, and S prime is the encoding of the starting state, F prime is the encoding of the final superstates, and finally in delta prime you're going to see our superstate transition function. So I'm going to walk you through the transformation that we do on the following NDFA. So first thing that we do is we need to compute empties for each state of the NDFA. So we're going to start with S, for example. There's my pointer. So S with consume no input can only stay in S, so that we're going to note as an empty of state S. But for example, D, when consume no input, can either stay in D or go to S. So empties of D are D and S. And we're going to do that for all the states in the NDFA. Now, there's our actual superstate transition function. So the way we do this is we start with empties of S. So our starting superstate is always going to be empties of S. And we're going to see where we end up when we consume all the possible input this NDFA can consume and take all of the empties as well. So S, starting superstate, on an A in the NDFA can go to A, B, and it's empties. So empties of A and B on an A are just A and B. So we note that as our next superstate. On a B from S, we can't really go anywhere. So we're going to put empty, and this in our building DFA is going to represent a dead state. Now we take AB, the superstate that we created, and take that as the next superstate that consumes some input. So on an A from A and B, we can't go anywhere. So we're going to note that as a dead state, so as empty. And on a B, we can go to C, D, and empties of them, so S as well. And that's going to be our next superstate. Now we can keep doing that for CDS and for all the other ones until we start having repeated superstate, and that's when we know when we're done. And our last row is just going to be transitions from the dead state, which are always just going to be into the dead state. So another thing we can do is we can encode these superstates to make them more readable. So all of the superstates that we gathered in the previous table, we're going to name simpler names, and finally the empty one we're going to name the dead state. So from this diagram here, we end up getting this diagram. So these are the encoded superstates and the dead state that we have in the DFA, and these edges are all of the edges that we saw in our transition function in one of the tables. So in our visualization tool, we build two-state diagrams at every step. The NDFA diagram is always fully displayed, and the DFA diagram is built one edge at a time. Now, a thing that we've done that's new is we can step backwards. So before I move on, I have to warn you. I had some misconceptions when I came to this conference. I thought everyone was going to understand everything I'm saying, and I realized I'm throwing too many names at you. So just whatever you see now, it's going to be catchy names. They all sound similar, but they all have different meanings. So just pay attention because we're going to be using them. So our NDFA diagram is partitioned into three color-coded subsets. We have hedges, which are highlighted edges. And these are the edges of the NDFA that go into constructing the edge of the DFA that we're currently building. So those are the corresponding edges of the DFA edge that we're building. Then we have fedges. Those are faded edges. They're faded out in gray, and those are the edges that have been used to build previous edges of the DFA that we built. And finally, we have bledges. Those are black edges, and they are yet to be used to build an edge of the DFA. So here are them all together in the same machine. So 3 fedges right here, and a hedge, and a bledge. Now I'm going to show you the visualization tool, and you're going to see everything way more clearly. Okay. There we go. So this is our visualization. As you can see, the NDFA transition diagram is fully displayed with empties of S highlighted because that corresponds to the starting superstate in the DFA. Here we see that the DFA just has the starting superstate when we start, same as in JFlap. But if we step one step through the computation, you can see that in the DFA, an edge has been built and a message is displayed of which edge that is. So we have FS on an A to AB. Now look at the NDFA. S, empty transition F, is now faded out because we're not using it anymore, but it has been processed. So it is a fedge. And S on an A to A or B is highlighted because these two edges of the NDFA correspond to this one edge of the DFA. So another thing that you might notice is we decided not to encode the superstates because we thought it would be important for students to see exactly which states of the states that correspond in the NDFA, which ones correspond to the superstate in the DFA. So we left that not encoded. So these two are still bledges because they have not yet been processed. But if we step again, so this edge, FS on a B to dead state, obviously leads to the dead state. But you can see that nothing is highlighted in the NDFA, because in the NDFA, there's nothing that corresponds to the dead state. But these edges are still faded out because we're done with them. And these are still bledges because we haven't processed them yet. We can just keep stepping one by one, or we can complete in one step. We can complete this transformation at any point of the transformation. So this is a fully displayed DFA diagram. We're still going to get a message with the last edge that has been added. In this case, this is this B on a B to B. And as you can see, the corresponding edge, B on a B to B, is also highlighted. Everything else in the NDFA is a fedge now because they're all processed. The entire DFA diagram is built. And there is no bledges anymore because we've processed everything. Now what we can also do is step backwards. So I just removed the B on a B to B edge that was highlighted, and the next to last edge becomes highlighted in the DFA. This one is to the dead state, so you're not going to see anything highlighted in this NDFA. But this edge that used to be highlighted in the NDFA is now faded out because we're not using it. We can step all the way to the back of the computation, so to the mere beginning. And we can just play around with the buttons. We can complete it right away, but that is the visualization. So this is our implementation. It's important for us to keep track of two things: processed edges and unprocessed edges of both NDFA and the DFA. Now these three are probably already familiar to you: fedges, hedges, and bledges. So fedges and hedges are processed edges of the NDFA, and bledges are unprocessed edges of the NDFA. U-pedges are unprocessed edges of the DFA, and pedges are the processed edges of the DFA. I told you it's going to be a lot of names. And we keep all of this in a visualization state structure. So instead of bugging you with this big chunk of a code, I'm going to show you what happens with these processed, unprocessed edges in a more visual form. So when we move the computation one step forward, one edge from the unprocessed DFA edges becomes a processed DFA edge. So in this case, it's that edge, AB on a B to B. That one gets moved from unprocessed to processed edges. And in the DFA, every one step forward, it's always just going to be one edge moving from unprocessed to processed. In the NDFA, we have a function that computes corresponding edges of that edge, so hedges. It computes them and highlights them. And whatever we add to highlighted edges, we also add to processed edges. And bledges, again, every time we step forwards, we take away from bledges because they're unprocessed and we process the part of them. And we add to fedges because fedges are also the processed ones. If we move one step backwards, we just reverse everything. So in the case of the DFA, we just take away one edge from processed and move it back to unprocessed. See this one? This one has now disappeared because it went back to unprocessed. In the NDFA, we recompute hedges for this edge to correspond. We add back to bledges because we went step backwards, and we take away from fedges. And finally, when we complete the transformation in one step, there's no unprocessed edges in either of them. So for the DFA, everything is in fedges or processed edges, and in the NDFA, now everything is in fedges. Everything's faded out because we're done. There's no bledges, and these hedges are highlighted. Now, there is cases where the last edge of the NDFA, actually the last edge added to the DFA, might be the one to the dead state. So if that's the case, all of this would be faded out and nothing would be highlighted. So this tool is very useful for students because we can easily determine why the superstates exist. And we accomplish that by not encoding the DFA graph. So you can clearly track which superstate corresponds to which states in the NDFA. We can see how all the NDFA edges are being processed by color coding them. Again, fedges, hedges, bledges. So at first glance, the student can see exactly which edges of the NDFA are using to build, which edges of the NDFA have been used to build, and which edges are yet to be used. And we can comprehend the development of this transition function, and we accomplish that by stepping one by one and breaking down the problem for a student to see the building of the DFA exactly how they would have probably done it. And again, we can move backwards. Okay, so this is an interesting thing that I've done the other day. I decided to run both JFlap and our visualization on the same machine. I chose a little more complicated machine, the one that I demonstrated in JFlap, and I decided to run both of them 10 times to see what I get every time I complete a graph in one step. So this is the first run for our machine on the left and JFlap on the right. This is the second run. This is the third run. Fourth, fifth, sixth, seventh, 8th, 9th, and 10th. So as you can see, JFlap graph keeps changing with every completion, and our transition diagram stays the same. This is also because GraphViz has a great algorithm for placing these states. So thank you, GraphViz. And finally, our future work includes adding visualizations for other transformations and constructors. We want to stay consistent with this because from experience, we've seen that students work the best in a predictable environment where they know exactly what to look for, at least in tools that they're using in their education. So for transformations, we're going to focus on NDFA to regular expressions and regular expressions to NDFA. And for constructors, we're going to do closure properties under union, clean star, concatenation, etc. If you want to learn more about programming in FSM and the transformation, you can get this book. It comes out later in fall. It's called Programming-Based Formal Languages and Automata Theory. Hey, we don't know if anyone was late. And it's written by Marco. And if you want to know more about the implementation of our visualization tool, you can read our paper. Thank you for your attention.
All right, what questions do we have?
Another great talk. I'm an outsider, so this is very useful to me. I've learned a lot. I noticed that both you and the first speaker used the term student as your user. Is there a reason why this wouldn't be useful for experts that are trying to debug their programs?
No, absolutely. Experts can use it, but the reason why we use the term student so much is because right now, most of the people that use FSM are Seton Hall students.
Sure.
So the experience that we have with people using it is mostly students and our classmates. We're using it too for our classes. So yeah, that's why we use the word student.
Okay, so it would be equally useful
Yeah,
for
absolutely.
programmers in general.
Absolutely.
Great, thanks.
Thanks. You you described the development of the deterministic automata as a sort of step-by-step process. You can step forwards and you can step backwards.
Oh, I thought you told me to step forward. I'm sorry.
No. So your visualization steps forwards and backwards, right? But in fact, each step you've chosen one particular input symbol to choose, right? So there's more of a branching structure. You could imagine the student exploring it could say, oh, what would happen if I consumed a B next? Isn't that right? It's not really a linear sequence, is it? Or it doesn't need to be linear. At any point, you could make multiple choices. You'll always end up with the same machine in the end, but it would sort of show up in a different order. Is that right?
Well, as a student, I'd always rather have it structured, even though I can't control it, than have unlimited, especially someone who's learning it for the first time, than having full control over what appears next, but not really knowing how to use it. So I'm pretty sure we add the edges in the order of the transition rules that we write. So we still have some sort of control over it because the entire visualization implementation works based on the machines that we construct, so based on the transition rules that we write first.
But you can imagine that once a student had got used to how it went, they might be interested in the idea that, oh, well, if I explore these in a different order, I still get the same machine at the end.
Exactly, they can tumble them down if they want to.
So it'd be great if you could, give them that control.
Yeah, I think they can do that.
On their second or third time through.
Sorry?
The reason to do it this other way is because our colleagues who study these things in cognitive learning say that the extraneous overload to learn how to use the tool has an impact. And so if you limit their choices, the extraneous load is lessened. That's the real reason. But of course, one could imagine a different tool where you can pick.
This tool. Once they've got the idea, so their cognitive load is down, they internalize that. Just an idea. Exactly.
If I understood correctly, though, you all consume them in the order that they're written linearly in
Yeah,
the
exactly.
automata?
Exactly.
So you could
Students-
also just go reorder your automata and get the same behavior.
It depends on them and how they design.
Yes.
Hi. Had a question. You can go backward in your visualization. I was wondering if you did like a clever trick, so you start from the state and you figure out how to go backward, or if you just record the state when going forward, then you just restore them. Well,
Okay, the
to
way
go
we
back.
go forwards and backwards, I was going to put the code in, but it was too big, and it would just be in code overload. So the way we go forwards and backwards is that we keep moving. We have a list of rules that the student designed in their machine, so that's what we're working with. And we're moving them from process to unprocessed. Of course, we have some functions that compute what's highlighted to the correspondent edge and stuff like that, but mostly it's just moving it around between the two lists. So that's how we go backwards.
Okay, so you don't need to record the history and restore history. You can go back from the rules.
Yeah, and it's always going to be the same as once the student designs the machine, it's the same order of rules every time when you run it on that machine. If you retumble the rules, it's going to be a different order, but the machine is while the visualization is running, the order is going to be consistent.
That's cool.
Thank you.
Hi, thanks. Great talk. This tool, I think, would be super useful at other universities as well. Is there a place where we can find the source code, or would we find ways to implement it in the book?
Okay, so in our paper, we included the GitHub link for FSM and downloading of the full thing. I think this tool is yet to be implemented at FSM, but soon it'll be there. So, yeah, stay
Thank you.
tuned.
Just real quick, how did you get Graphviz to keep your layout stable? When I use it,
Graphviz
it
does
doesn't
that
do
by itself. It's awesome. Graphviz has a great algorithm for that. I don't even know what that algorithm is, but it's pretty cool. Never had a problem with Graphviz. Oh!
Other questions? And let me go check the internet.
Might be a good tip. The way, I don't know how you use Graphviz, but the way I used it in this visualization tool is I always lay out the two functions, first to design nodes, and then I take that as an input, that graph, for the function that designs the edges. So I first create the nodes, and then I create the edges using that graph as input.
All right. I guess, again, chair privilege, I'm going to take the last question. It's really cool once I've got the DFA out at the end. Is there some way, either through the GUI or through the REPL, to save that? Because I can imagine wanting to now use this DFA with some other one in an epsilon transition and go through the process again.
I think we're working on that right now for the FSM Visualize. So we add this tool into FSM Visualize, but more about that a little later.
All right, let's thank our speaker.